Hi everyone, my name is Bill, and today I'll be talking about KNN theory and something really interesting about machine learning algorithms that I found out when I was researching theory related to KNN algorithms. So KNN algorithms or K-nearest neighbor algorithms are traditionally seen as a pretty simple algorithm in the scope of machine learning. But in this talk, I will prove something about its convergence and its performance. And I think combined with the something very interesting that I discovered or that I studied when I was learning about KNN theory, I think it provides some very interesting insight into statistical learning in general. So during this talk, I'll go over four main parts. First one is I'll set out the assumptions and notations for the algorithm that we're using. Thankfully, because of how simple KNN is, this won't take long. Then I'll be talking about KNN convergence, and then I'll be introducing something called a no free lunch theorem or the NFL theorem. I find it really funny because it's like the National Football League. The NFL for the NFL theorem basically states that a priori all algorithms have the same loss, or the average loss across all possible problems are the same. And I'll talk about that later. And then I'll talk about some other uses of KNN in opposition to the more conventional way of using KNN. So when we're talking about the K-nearest neighbor algorithm, our core assumption here is that similar inputs have similar outputs. So this is often, I would say this is often ignored in practice, because we think that it's a very simple algorithm, but in fact, it might lead to really big problems, because when we're actually calculating maybe like the norm or distance between 2 points, we already assume that their outputs would be similar, when we're not really looking at how similar the 2 points already are, even though maybe in probability terms, what we would say is we are already conditioned on the fact that 2 points are very similar, but we're not even looking at the actual distance of the 2 points. And this will cause issues that I'll talk about later. And when we're doing KNN algorithms, I'm just saying it right now because we are discussing about the assumption. So for notations here, I'm going to take the point of interest, or the point that we're trying to find the nearest neighbors and do the analysis on, as K. And we're going to assume that the parameter of interest or the dependent variable that we're looking at is Y. We're gonna set the sample space to be D, and let the dimension be N. Due to the nature of KNN, when we're finding the K nearest neighbors, we're gonna set that set of such neighbors to be Sx. And for the distance function, we're just going to use the Minkowski distance. All norm functions, or at least all common norm functions, follow Minkowski distance notation. And for the classification function, we're just going to call it the mode function of all y's where the corresponding x is a part of Sx. Here, the classification function, I use hx because we can also call it the hypothesis function. So first of all, what I would like to prove is that the nearest neighbor does actually converge to the actual point that we are interested in. So that goes back that ties back to the assumption that similar inputs have similar outputs. I guess you can imply that if the inputs are not similar, then the outputs are not going to be similar because of our assumption. So it's very important that we actually set the nearest neighbor to actually be near. So here we show that the neighbor will be near, or it will converge to x in this point. So our formal definition is as n approaches infinity. Oh, here I wrote 0. It's as n approaches infinity, the probability of the distance between the nearest neighbor and the point of interest being greater than a set epsilon value is 0. So here we're saying that it's as n approaches infinity, the probability that the nearest neighbor diverges from x is 0, so it converges. So so here the main proof is that when we're saying that the nearest neighbor is close enough to the point of interest, so we're basically saying is that every other point is at least farther than x. So we can rewrite p absolute value of xn minus x greater than epsilon as the fact that all points are as far to x as the nearest neighbor is. So that's just the product series of xi minus x greater than epsilon. And we can rewrite this function as instead of looking at the probability of being greater than epsilon, we look at the probability of being less than epsilon, less or equal to epsilon, and then subtracting 1 by that. Another assumption out here we use is that we are talking about a really small epsilon, and that makes sense because we're trying to prove that the nearest neighbor converges to the x. So in a small enough ball for any element, so let's call it u being part of the ball, let's call it b. Fu will approximate to fx. Let's assume that. And if we set that assumption, then we can just rewrite the probability that we previously defined as an integral. And since the item in the integral is always the same, here fx, and fx is independent of the variable that we're integrating over with, which is u, we can just take out the fx, and given that it is a ball, we can just set the value up. We can approximate the value to be c times epsilon to the power of p times fx. Fx is the value that we originally integrating over with, epsilon to the power of p, because this is a ball, we have p dimensions, and the radius of the ball is epsilon. C is just a modifier that we have. For example, for 2D, it would be like 2 or 2 pi. For 3D, it would be 4 over 3 times pi, etc. We're not really interested in the value of C here. So we can reassign the previous probability with this value, and we can see that when epsilon is small, p is very large. Epsilon to the power of p approaches to 0 as epsilon approaches 0. So the previous result, we can further simplify it to 1 minus n times c times epsilon to the power of p times fx, similar to how engineering students approximate the sine function, and this approaches 0. So what we have with this is that the probability does approach to zero when we assume that the ball is small enough, or in this case when we assume that x when we're looking at when the nearest neighbor converges to x. So looking at the previous function, we can also actually get a rate of convergence for the error. So if we set the error to a certain goal, for example, like delta, then we can just reassign. We can just do some algebra, some really basic algebra, reassign variables, and we can get that the epsilon equals n to the power of -1/p times times some other stuff. And what this means is that epsilon converges at a rate of n to the power of -1/p. So this is very important because now we know that 1 and n or the nearest neighbor, or here what we call the 1 and n, where it's just k and n where k equals 1, it will always converge to the true value that we're searching for with a large enough n. So so now after we establish that the nearest neighbor does converge to x, we want to prove that the algorithm itself actually converges to the true value. So here we're assuming that the data has noise, and which is always the case. And first of all, we can say that the error rate for this 1 and n algorithm that we're looking at right now is capped at twice the error of the Bayes optimal classifier. So the proof of this is relatively simple. Let's just introduce some new variables. Let x and n be the nearest neighbor for x. Then, as we previously established, as n approaches infinity, x and n approaches x. So here, let's just assume that x and n is identical to x, and what we have is the error value. For example, for a classification function, this is the probability of y condition on x times the probability that the x and n result is wrong, plus the probability of y condition on x and n, which is the nearest neighbor, and times 1 minus when we wrongly estimate x y based on x. So what we do here is symmetry, because x and n is identical to x. We can just combine the two. Two products to get the final the final result 2 times 1 minus the probability of the conditional probability of y given x, which is just the error for the Bayes optimal classifier. Here we can use the less than or equal sign, because we know that the probability is always between 0 to 1. So here we have an error bound for the case where we're looking at only the nearest neighbor, or the 1 and n case. But what about when k is greater than or equal to 2? So here let's look at the case where k is greater than or equal to 2. And for simple and without loss of without loss of generality, let's just look at the regression case here. So the regression case for k and n is where we just find the nearest neighbors and we just average the values. So obviously we can convert this to a classification case if we just set the value to be the identity function. So so for regression, let's just assume that the Gaussian error term to be 0. Then it becomes a very simple fact that the predicted value that we have is just the average of the true value plus the average of mu plus the average of epsilon. So and fortunately for the case of k greater than or equal to 2, we still only have to look at one of the nearest neighbors, and here we're just going to look at the largest nearest neighbor. So for example, if k equals 2, let's look at the second nearest neighbor. The ball, so for if k equals 5, let's look at the fifth nearest neighbor. And the reason of that is assuming that that kth and nearest neighbor is in a small enough ball, all other nearest neighbors are already in the ball. So here, let's look. So here we can see that since k over n still approaches 0, compared to the proof is the same as the previous case, because we set the question such that because we set the question such that we are still essentially looking at the same case as in the 1 in n case. Another thing that we will want to note that is that the variance of the epsilon value is just the bias over k. And this is very important because if we look at the bias variance split off of the KNN, we see that the KNN error bound is just the noise of the data plus the approximation error plus the model variance. So previously we assumed that previously we found the model variance, and we said and the approximation error is 0 here because we are assuming, remember, that similar inputs have similar outputs. We can see that the error for the k case or the KNN case is just sigma square of sigma square of x plus 0 plus sigma square of x divided by k, which is just 1 plus 1 over k times sigma square x. And note that sigma square x is also the error for the Bayes optimal estimator that we previously mentioned. And what this says is that, so for example, in the previous case where k equals 1, the error is just 2 times the error for the Bayes optimal estimator, and that is exactly what we proved previously. Another thing that I find really interesting about this is that for k, when it approaches infinity, our KNN model will perform as well as the Bayes optimal estimator. However, in practice, we are limited by the curse of dimensionality. And actually, if we say that k approaches infinity, it actually might violate the core assumption that we previously talked about, which is similar inputs leads to similar outputs. Because as the dimension of data increases, the more spread out the data points are. And what happens when the data becomes more spread out is that the data set becomes more sparse, and each data point between each other becomes less similar. And remember when we talked about the fact that the core assumption for a KNN algorithm is that that the outputs are similar for the KNN algorithm only when the inputs are similar. So one way to solve this is that let's just add more data points. But there are two main problems with that. And first one is, in reality, often we only have limited number of data. And as Olsen says, if we have data for everything, we don't need statistics anymore. Another issue with that is, as the dimension of the data increases a lot, we will need a lot more data points to quote unquote guarantee similarity between the space. So for example, if we're looking at only a 2D number line, the amount of data that we need to ensure a similar amount of sparsity or similarity between the data points when we expand it into, for example, like a 3D space would be twice the amount, instead of increasing linearly. So in practice, what this means is that when we're doing KNN, we will often have to shrink the dimensionality of the data set. And as in a lot of cases of machine learning, shrinking dimensionality is often more of an art than a science. Of course, we have a lot of ways to do that, for example, like PCA, but in the end, that all depends on the specific problem or the posterior of our data set. And speaking about posterior of data sets, what I want to touch on is the no free lunch theorem. So remember how I said in the beginning that under certain cases, the KNN algorithm will perform as well as the most complex model that we ever created. So previously, I proved that is the case when we set k to when we let k approach infinity, and I find it really interesting because KNN is a very simple model, and somehow, theoretically speaking, it might perform as well as a highly complex model. And when I was researching on this, when I was researching on this, the main idea that I found out was that this theorem called no free lunch. And to quote it, the no free lunch theorem states that any two optimization algorithms are equivalent when the performance is average across all possible problems. So what we mean by all possible problems is, let's just take an example of the classification problem. So if we have two items to classify, then the problem set that we the term all possible problems just means that we have four possible problems. For the classification case, let's just use 1 and 0 for the output variables, then that would be 1, 1, 1, 0, 0, 1, and 0, 0. So that's what they mean by all possible problems. So to put it in mathematical terms, let C be the risk function, let D be the training set, let N be the number of elements in the training set, and let F be the function that be the posterior function to approximate the relationship. Then Wolpert proved that a priori, the expected value of the risk function, condition on the training set, condition on the number of elements in training set, condition on the posterior, condition on anything, the risk function, the expected value of the risk function, when averaged, will be the same for every possible algorithm. So due to time constraints, I will not put out a detailed proof. One way to think about no free lunch theorem is a quote that David Hume, the Scottish philosopher David Hume, once said, and in fact, Wolpert quoted him in his paper. And right in the beginning, David Hume said is that even after the observation of the frequent or constant conjunction of objects, we have no reason to draw any inference concerning any object beyond those of which we have had experience. And to put it in simpler terms, he just means that be cautious when you're doing extrapolation. But in terms of theory, I'm just going to put down the main idea for Wolpert's proof in his original paper in 1996. And the main idea of proof is that because the cost function is symmetric, when we're averaging the cost equation over all possible conditions or posteriors, we can actually omit the parts which include the specific algorithm that we have, because it is symmetric. And when we omit all when we omit all the terms in the cost function, in the cost equation, that includes the specific algorithm that we have, what that means is the cost equation for all possible algorithms are the same, because we took out the only variable that might differ across all the cost equation calculations. And that just means that the average cost equation is the same for every algorithm. So given that we have this theorem, I think we might enter into a philosophical paradox here, and it's that the 1NM algorithm that I previously mentioned, which might be the most simple machine learning algorithm, will perform quote unquote as well a priori as even the most complex neural network. And it might sound and it might be an irony that for both algorithms their abbreviation is NN. But the author also says that even though that is the case a priori, in reality, every individual distribution that we're trying to approximate using statistical learning method has its own posterior distribution. So for each specific question, this algorithm will be the one that models the posterior distribution the best. And because we have the posterior distribution, we have a specific posterior. So what he means is that because we have a specific posterior distribution, we are not looking at the average of the algorithm, or the average cost function of the algorithm over all possible posteriors. We're looking at specific posteriors. So the means does not equivalent to a specific case. And in the end, I was talking about how simple the KNN is, but there have been a lot of ways people made up to make the KNN algorithm more complicated. So here I listed 4 different variations of KNN where the KNN algorithm becomes more complicated than just simply finding the mode. So for adaptive KNN, we find the optimal KNN we find the optimal K for each training data point. Then we find the nearest neighbor for the data point that we're interested in, and we use the optimal K for that nearest neighbor to conduct the KNN algorithm. For fuzzy KNN, we assign a fuzzy membership value for each class that we're trying to that we're predicting the value from, and then we just pick the class with the highest value. For k-means KNN, we apply k-means to the data set, and then we find the nearest neighbor for the data point that we're interested in, and we just use the centroid for that specific point for classification. And for weighted KNN, we use a kernel function to create a weight for each data point compared to the data point that we're interested in, and we use this kernel function weight as a weighted function to calculate the predicted value for the data point that we are interested in. And I would also like to link it back to research that I was doing. So this is a lasso method called fused lasso. So for regular lasso, for regular lasso, we use lambda times the absolute value of beta as a constraint term. Or if we expand it to matrix form, we're just using lambda times identity matrix times 1 norm of the whole beta vector as a constraint term. But here we use lambda times g instead of I as the constraint term, and we can set g to be any matrix. So for the KNN fused lasso case, we use the KNN graph for g. And what I mean by the KNN graph is it's just a graph where it identifies which data points are the nearest neighbors. So so you can think about the identity matrix as sort of a KNN graph where we allow the data point itself to be calculated with to be calculated as a potential candidate for the nearest neighbor, and we set k equals 1. So this is useful for many occasions, such as contour regression or image denoising, etc. So in conclusion, I proved that the error of the Cannon algorithm is bounded by 1x the 1x the risk of the Bayes optimal classifier and 2x the risk of the Bayes optimal classifier. And we established a condition where the Cannon algorithm approximates the Bayes optimal classifier. Further on, given this insight, I showed how a priori KNN and not just actually not just KNN will perform just as well as any other algorithm. However, note that in practice this is not the case because we're not talking about the average cost anymore. We're talking about specific cost for a specific question. And I also briefly mentioned ways where we can implement or we can change the implementation of the KNN algorithm into other ways. So to better serve the question that we have.
Okay, is that the end?
Yeah, is that 30 minutes?
Yeah, I mean, you finished, right? Yeah.
Yeah, I wanted to include a more specific proof of the NFL theorem, but later on when I was doing rehearsals, I realized that that would take too much time.
Okay, that's okay. I think it was like enough material for a 30-minute talk. So, okay, thank you. Any questions? Okay, so I can make some comments. First, I mean, some of the theory for the KNNs we have done in class. So maybe if you go back to prove the consistency of KNNs in the context of regression, when we talked about the Stone's theorem, and then also you drive rates. So some of the proofs that you did was a little bit hand waving. There was some hand waving involved, so maybe you could make it more precise in your. So if you go back, for example, to the slide that you proved that KNN achieves like at most twice the base. So this is so saying that as n goes to infinity, then nearest neighbor converges to x, and then we replace this with x. This is not it's not precise, so you have to be a little more precise, right? So you can't just say we and then you have to be like careful what the risk is actually. So is x is fixed, random? Maybe maybe try to like make this a little bit more precise, right? We can't just replace things with the limits and then say that that's the error of the KNN, right? There's the approximation error. So you have to say, or some sort of, you have to do some sort of argument that whatever you're like doing, like at least be continuous in x, or just make it more precise. Do you see what I mean?
Yeah.
And then some of the notations also, like if you go to the slides, the next slide, the notation, I think we have to be a little bit careful. Right, so for example, yn and xi, that is, so what is xi here? So there is some sort of a dependence on x here that we have to be careful.
Yeah, xi is just the set of the multiple neighbors.
But that would depend on x, right? So there's like x on the left-hand side, but not on the right-hand side. So if you like try to make the notation more precise, it would be helpful.
Okay.
Because the regression function would depend on x, and the set of xi's would vary with x. So it helps like the nearest neighbors. So if you look at the lecture notes or like the slides that we went over, we used some notation, try to have like there's some literature trying to write it's hard to write the KNN's sort of estimate in symbols, but there are ways of writing it which makes it more explicit, the dependence. Okay. And then one comment about the no free lunch. What was your take on? So it's like the KNN is the same as neural networks or like any other method?
Yeah. So I mean, no free lunch just says that a priori, the average cost of of any algorithm over the set of all possible problems is the same.
So a priori respect to what? So what changes things then?
Oh,
So why should we
we're
use
only
any other method? So I can do like random guessing. So you're saying random guessing would be equivalent to doing like sophisticated machine learning. That would be
uh
what would you say? Why would like not flip a coin?
yeah yeah. So we're not. So I mean, like, so for example, like what the theorem says is that, say I can flip a coin and just decide something, on average, or the average risk, or the average error function or risk function that we have over all possible problems that exist in the world would be the same. But if we're looking at a specific function, um, because if we're looking at a specific function, if we're looking at a specific problem, the problem that we have like an actual case where the data follows a set of assumptions, or it follows it has its own posterior distribution. So in that case, we would have a specific algorithm that best approximates the actual data set that we have.
Okay, yeah, so that makes more sense. So yeah, so you have to sort of interpret these results. Some part of it is not, it's interesting, but it's not that relevant. So we don't average, for example. So you never see the average. Oh, so the average would happen if you like do a lot of these things and you care about, let's say, you're doing it over any like a lot of problems and all possible problems, and then you care about the average risk over all possible problems. Um, and if you put some regularity on the problems, like just assume that, for example, the regression function is smooth, then it would break this result. So if you think you know something about the, for example, regression function, then you can prove upper bounds and lower bounds. So we did this in class. So you could show that you can actually consistently estimate the regression function. So this result would say basically regression or estimation or classification is hopeless because I could just do random guessing or something like that, which is not true, which is in practice. So the question is that what does the average risk over all possible problems mean, and whether you care about it. That's the thing. If you average over a subclass of problems, perhaps that would make more sense. But so I would say maybe go back to the things that we discussed in class. So for example, you can show that you can do universal consistency. So if you fix a problem without much assumptions, you can provide estimators that consistently recover the function without just the assumption of finite moments is enough. So that was the first half of the course. So you showed that you could, for a fixed, if you have a fixed regression function, you don't need to impose assumptions. You can recover it by, let's say, KNN if k goes to infinity and k over n goes to 0, and various other methods. So the thing is, try to maybe balance it out in your report. Try to just place it in the right position. It's not saying that it's not something that you have to like. So you have to understand what it is saying, and it's usually not that useful in practice. So does it make sense?
Yeah.
Yeah, just go back maybe to the discussion of universal consistency. You can recover things universally. The thing is, try to reconcile that with this, and there should be no contradiction. There's no contradiction, but try to maybe, yeah. Okay, thank you. Interesting discussion. Any other questions?